Today we're going to solve a very interesting problem, and I actually like this problem because we're going to use several very interesting and very useful facts, and those are the facts that you probably want to know when you're solving geometrical problems. So what we have here is a circle, and we have a pentagon which is inscribed into the circle. We know two angles in this pentagon, angle of 90 degrees here, angle of 100 degrees. We also know that there are two angles that are congruent to each other, and we were asked to find these angles. The other thing is that mysterious segment BO, which is not really clear why it's here. But it turned out that it served a purpose, and there's a fact that BO is actually parallel to side CD, and that's an important property that we will use to solve this problem and to find angle X. So what can we do here? We have a polygon here, and we have some angles in the polygon. We also asked about angles in the polygon. So probably knowing the sum of all angles of the polygon would be a good thing to know. And we know a very good and very important formula about the sum of internal angles of a polygon. So if our polygon has n sides in n angles, sum of all angles of the polygon will be 180 degrees times n minus 2. Normally this formula is proven in geometry courses for convex polygons. But in fact, this formula is true for any polygons, convex or non-convex. So very good, very useful. Let's call this angle C here as Y. And now we're going to add all these angles of the pentagon, and that sum should be equal to 540 degrees because for pentagon n equals to 5. If we simplify this equation, this is what we're going to get. This is the relationship between x and y. By itself, we cannot find x from here because we don't know y. We need another expression of similar kind to actually solve a system of equation and find x. So the next thing we would like to use is inscribed angle theorem. So we have a couple of inscribed angles here, measure which we know. It's angle E of 90 degrees and angle D of 100 degrees. So let's remind ourselves what inscribed angle theorem is. So if I have a circle with center O, I can have the angle AOB, which is central angle, and that angle is intercepting the arc AB. Now, what I'm going to do, I'm going to choose a point C anywhere on the circle outside this arc AB. And now this angle ACB is going to be inscribed angle. And these two angles, this green inscribed angle and this blue central angle, are related to each other. It turned out that the inscribed angle is half the central angle. And what's also interesting about this formula is that formula will work for any central angle from 0 to 360 degrees. So angle AOB could be more than 180 degrees, and that's not a problem. There's one specific case of the inscribed angle theorem, and that is often called Thales theorem. And that's the case when inscribed angle is 90 degrees. In this case, central angle has to be 180 degrees. And that means that AOB are going to be on the same line, and that line is going to be diameter. And if you look at our picture, we do have an angle of 90 degrees here, angle E. And that means that points A, O, and D lay on the same line, and that line is diameter. The next thing we want to do is to use this property somehow. We have BO parallel to CD. We also have a line BC, which is transversal. And we know something about the properties of some angles that you get when you have parallel lines intersecting a transversal line. In particular, this angle C, angle Y, and the angle right here, angle OBC, they're what's called same-side interior angles for parallel lines. And those angles together should give us 180 degrees. So this angle here, OBC, should be 180 minus Y. We know the whole angle here, B, is X, and we know right-hand side. So we can easily calculate left-hand side, which will be X plus Y minus 180 degrees. Now let's look at the quadrilateral ABCD. That is a special kind of quadrilateral. It's an inscribed or cyclic quadrilateral. And we know that quadrilateral is inscribed if and only if sum of opposite angles is 180 degrees. Look, here we have angle Y. So angle right here, or angle BAD, will be 180 minus Y. And now let's look at the triangle AOB. AO and BO are radii. Triangle AOB is isosceles. Angles at the base of an isosceles triangle are congruent, and that means that this angle right here should be equal to this angle. And that gives us this relationship. We simplify and we get an expression for X and Y. And now we have two equations, right here, and two unknowns. We can solve them. To solve it, what we're going to do, we're going to multiply the first one by 2. We're going to get this. And now we're going to subtract this equation from this equation. We get 4x minus x is 3x. 2y and 2y are going to cancel out. And we get an expression for x, which we can easily solve and find the final answer, that x equals 340 degrees divided by 3. So what we did today is we applied several useful facts to solve this problem. First of all, the sum of angles of a polygon. Second of all, inscribed angle theorem. There's a fact about inscribed quadrilaterals. And there are some facts about parallel lines and the angles that they create, and also angles for isosceles triangles. So if you know all these facts, you're actually good to go, and you're going to live happily ever after. The end.